All right, in this example, I'm going to give an example of finding a Jordan form of a 3 by 3 matrix as well as a basis for R3 that with respect to which the matrix A is in Jordan form. So the example is A is this 3 by 3 matrix, and the question says write A equals PJP inverse where J is in Jordan form. So the first thing to do is to find the eigenvalues of this matrix, and it turns out that the only eigenvalue is 9. And this can be found by calculating the characteristic polynomial of A, which we're not going to do because it's a 3 by 3 matrix, it's a mess. So the first thing to show is that the only eigenvalue of this matrix A is lambda equals 9. So once you know that the only eigenvalue is 9, there's only a few possibilities for the Jordan form J. It could be, well, it's not going to be, but potentially, I mean, in theory, if you just have the Jordan forms of a matrix with eigenvalue 9, it could be this. Now, we know it's not going to be this because if J were that, then PJP inverse would just be J. And A is not equal to J. So we know this is not going to be possible, but I'm just going to write this out. It's that, or it could be, so this would be a sum, this would be a direct sum of 3 Jordan blocks. Or there could be 2 Jordan blocks, one by 1 Jordan block, and then a Jordan block like this. Or it could be 1 Jordan block, which is when you have ones directly above the diagonal. And the question is, which one do we have? Well, for the 3 by 3 case, it doesn't happen in the case of n larger than 3. But in the 3 by 3 case, we can actually distinguish these by looking at the rank of J minus 9i. So in this case, J minus 9i has rank 0, right? Because it would be the 0 matrix. In this case, J minus 9i has rank 1, right? And J minus 9i in this last example has rank 2. And the key fact we're going to need is that the rank, so the first step of finding the PJP inverse is to find J. And so we can use the fact that the rank of A minus 9i is equal to the rank of J minus 9i. This is more or less an exercise because the idea is since A is similar to J, the rank of A is the same as the rank of J, and actually, let me try this again. Since A and J are similar, the fact is that similar matrices have the same rank. Now, A and J are similar, and that implies that A minus 9i is similar to J minus 9i. That's a relatively easy thing to show. And therefore, they have the same rank. And that's the explanation behind why this equation is true. And so to figure out which J we have, I mean, we know it's not the first one. So it's either this one or it's this one. To figure out which one it is, we can calculate the rank of A minus 9i. And if the rank of A minus 9i is 1, then it's this one. And if the rank of A minus 9i is 2, then it's that one. Notice, alternatively, we can write this second one as, we can always rearrange the Jordan blocks. So it could be like this. Okay, where you just switch the 2 Jordan blocks. It doesn't matter. Yeah. Okay, so what's A minus 9i? Well, A minus 9i, we're given A, so that's easy, if you subtract 9 on the main diagonal, we get 1, 1, negative 2, 0, 0, 3, negative 1, negative 1, negative 1. Now, it might not be apparent. Certainly, the rank is either 2 or... let's see. Oh, wait, we already know what this is, right? Because the rank is not... I can see that the first 2 rows are not scalar multiples of each other. So certainly this has rank 2. We know this matrix doesn't have rank 3 because we know that since 9 is an eigenvalue, A minus 9i is non-invertible. So this matrix has either rank 1 or 2, and it certainly doesn't have rank 1, and therefore it must have rank 2, and therefore J must be this. Okay. By the way, some books put the ones directly below the diagonal instead of above. But I think it's more typical to write the ones above. Okay, so that's J. And now we need to find P. That makes A equal to P times J times P inverse. Well, the idea is, if you watched my video on the 2x2 case, we have AP equals PJ. And so if we denote the columns of P by V1, V2, and V3, we have A times that is equal to this times J, which is this. And now we multiply the matrices together, column by column. The columns of this matrix are equal to the columns of that matrix since they're the same matrix. And if you look at the columns one at a time, the column on the left, the first column is A times V1, and remember that to multiply 2 matrices together, you take linear combinations of the columns on the left. So this is going to be 9V1. Okay, are we okay on where we get this? Because you have 0 and 0. Well, let's just fill in all with zeros. So what you do is you take 9. The first column is 9V1 plus 0V2 plus 0V3. Right? So let's just... Okay. So that would be the first column of the matrix on the right. And the matrix on the left, when you multiply A by this matrix with columns V1, V2, V3, you get a matrix whose columns are AV1, AV2, and AV3. So when you set the columns of the matrices equal, the first column tells you that AV1 is 9V1. All right, what about the second column? Well, the second column on the left is AV2, and the second column on the right is 1V1 plus 9V2 plus 0V3. And the third column on the right is AV3. The third column on the left is AV3. The third column on the right is 0V1 plus 1V2 plus 9V3. And we need P to be invertible, and so we need V1, V2, and V3 to be linearly independent. And so what we need to find is we need to find a linearly independent set V1, V2, V3 of vectors in R3 such that these 3 equations are true. And once you get the V1 and V2 and V3 that are linearly independent and that satisfy these 3 equations, then you can make those the columns of P, and that will be your matrix P. Okay, so we just need to do that. Well, before we start, we can rearrange things a little bit. So the first equation, I'll keep the same. Well, that's really the same as finding an eigenvector, right, with eigenvalue 9. I mean, if we want, we can just write this as a minus 9I v1 is the 0 vector. And we can subtract from the second equation 9v2 to get a minus 9I v2 is v1. And then we can, from the third equation, take away 9v3 and get a minus 9I times v3 is v2. So you see, we really just need to work with a minus 9I. Once you find v1 from the first equation, we use that in the second equation to find v2, and then once we find v2, we use the third equation to find v3. Okay? So let's find v1 first. So for v1, we need to solve a minus 9I v1 is the 0 vector, and we just do an elimination. So a minus 9I we found above, and we just set up the augmented matrix, and I'll just do the line here, and we do the Gaussian elimination. So we want to put this into row echelon form. Well, the second row is okay, and then the third row we need to replace with row 1 plus row 3. And if we do that, we're going to get 0, 0, negative 3, 0. And so the third row is going to turn into a row of zeros, which we want, right? We should get a row of zeros because we know this matrix A minus 9I is not invertible. And then if you divide the second row by 3, we get this. And then if you want, you can just put this into reduced row echelon form. Okay, so the equations read x plus y is 0, z is 0. And we want a non-zero solution to this. Right, so we can just take v1 to be the vector, say 1, negative 1, 0. Okay. So that's v1, and now we need to find v2. And we need to solve a minus 9I, v2 is v1. See, sorry. Okay. Well, if you do that, I'm just going to skip to the end because I think we already know how to do this. If you calculate the row echelon form, you're going to get this. And so you solve x plus y minus 2z is 1, z is equal to negative 1/3. And so we get that x plus y is 1/3. And so one possibility would be to take v2 to be 1/3, 0, negative 1/3. That would be a possible v2. Now, this has fractions in it, which you don't want to deal with. And so what you can do is so if you go back to this system of equations here, if you scale v1 by a scalar, the system will still be true if you scale v2 by that scalar. And so in this case, if you want to get rid of the fractions, we can change the v1 to be the new v1 by multiplying by 3. And when you do that, so if you use 3, negative 3, 0, instead of this, if you use 3, negative 3, 0, here you would have ended up getting the new v2, which is 1, 0, negative 1. Okay, not super necessary, it's just that it cuts down on the computation because you just have integers and it's easier to work with. Okay, so if we had used v1 equals 3, negative 3, 0 instead of 1, negative 1, 0, we would have gotten v2 as 1, 0, negative 1. Okay, so let's just use those because they have integers. And finally, we need to find v3. Well, we need to solve a minus 9i times v3 is v2. And we're using the new v2, so we get this system. And this is actually relatively easy. I'm just going to skip to the echelon form. You get this. Okay. And so you get that the third component has to be 0, and the first and second components have to add to 1. And so we can just take v3 to be 1, 0, 0. And so that's our v1, v2, and v3. And so our matrix P is, and again, there's multiple possibilities because there's multiple possible v1s and multiple, even once you pick one of the v1s, there were multiple v2s, and once we picked the v2, there were multiple options for v3. But for the ones that we had v1 is 3, negative 3, 0. v2 is 1, 0, negative 1. And then our v3 was 1, 0, 0. So that's our P. The only final thing to check is we need to check that the columns are actually linearly independent. There might be a theorem that I'm not sure if it's true that they're automatically linearly independent. They might not be automatically linearly independent, but here we can, I think it's pretty easy to see that, okay, so if you change row 2 to row 2 plus row 1, you get this, and I see that this matrix does in fact have rank 3, right? So this matrix has rank 3, and so therefore the vectors are linearly independent. And so therefore our matrix A is going to be this matrix times J, which is, which we found to be this, times P inverse. Okay, so with respect to the basis B consisting of V1, V2, and V3, this matrix relative to that basis is going to be the Jordan matrix J. Okay, now there are, in more complicated examples, in theory it might be possible to come up with a V1 so that when you solve for V2, you actually get an inconsistent system. In that case, you would have to try a different V1. But eventually you'll be able to find a V1 that makes it possible to find V2 and so on. Okay, thanks for watching.